Welcome to the first video for MATH0007 Algebra for Joint Honours Schools 2021. In the first video we're going to learn a bit about set theory, about the notation and the vocabulary used in the study of sets. Let's begin with what is a set. So a set is simply a collection of mathematical objects. And the objects in the collection are called its members or its elements. And we have some notation for when a particular thing is an element or a member of a particular set X. So we write this to mean that X, little x, is an element of the set big X, and we write the same symbol crossed out to mean that little x is not an element of the set capital X. To specify sets in simple situations, we can simply list the elements of the set separated by commas inside curly braces. For example, this denotes the set whose elements are 1 and 2 and 3. So to give you an example of the membership notation, we would write that 1 is an element of the set 1, 2, 3. On the other hand, 0 is not an element of the set 1, 2, 3. Some further examples of sets specified in this way are this, which is the set whose elements are 1, the set containing 2, and the set containing 3. We don't restrict the mathematical objects which can be elements of sets. They can be numbers, they can be sets themselves, they can be vectors or functions or matrices. There's no restriction on the kind of things which we allow as elements of our sets. A further important example is this one. This is the set which has no elements at all. It has a special name, it's called the empty set, and there is an alternative and perhaps more common notation for the empty set, which is a 0 crossed out like this. So that denotes the set which has no elements at all. So in particular, no matter what x is, x in the empty set is always a false statement. Okay, moving on, and that's not the only way we have to specify sets. Often it's not possible to list all the elements, or it's difficult to do so in a way which makes clear what those elements are. In those situations, we use set builder notation. You took Analysis 1 last term, or at least most of you did, and so you will have seen various examples of this notation. So I just want to recap precisely what that set builder notation looks like and what it refers to. Here's our first example. We write set braces and then x and then a bar, or sometimes people will write a colon instead of a bar, meaning exactly the same thing, and then a description of a criteria for the element x to belong to that set. So we might write x and then a bar and then x is a real number and x is less than 0 and then close the curly braces. That means the set of all real numbers which are strictly less than 0. If you're familiar with interval notation, you might have seen this written as the interval from -infinity up to 0, open at both ends. On the other hand, we use this notation not just for sets of real numbers. Here's another example. We might write x and then a bar, and then x is a rational number whose square is less than 3, and the whole thing in curly braces, to refer to the set of all rational numbers whose square is less than 3. A rational number is a number of the form a divided by b, where a and b are both integers and b is not 0. We'll describe the set of rational numbers later. So that will be another typical use of this set builder notation. A common variant on this set builder notation is where you write curly braces and then x in capital X and then p of x, where p is some property which may or may not be true for a particular thing, little x. To see an example of this minor variant on set builder notation, we might write x in z, x is even. So here the property px is the property of being even. That's something which might be true or not for a particular integer x. And here z, I'm going to define this properly later, but this just means the set of all whole numbers, positive or negative. So of course what this refers to is the infinite set consisting of all the numbers -4, -2, 0, 2, 4, and so on. And this is a further example of our set builder notation. Okay, I promised I would explain some of these standard notations for sets of numbers. These are used all the time. This is a completely standard notation used everywhere, with one minor exception which I'll come to when we reach it. So first of all, this bold R, it's called Blackboard Bold, this font. That's the set of all real numbers. A real number is a number with a decimal expansion. These are the numbers that you deal with in analysis 1. So things like 0, 1, -7, pi, √2, -3/4. Every number with a decimal expansion is an element of this set R, which is called the set of all real numbers. On the other hand, bold C is the set of all complex numbers. Those are the numbers of the form x plus I, y, or the numbers which can be written in this form, where x and y are real numbers and I is the square root of -1. Where our notation gets slightly controversial is for the set of natural numbers, bold N. The reason this is slightly controversial is that for me, 0 is an element of the natural numbers. Not everybody thinks this way, so you will find a roughly even split in the literature between people who think 0 is a natural number and people who think 0 is not a natural number. So there's no correct or incorrect about this, it's simply a matter of convention. And for me, I like to use the natural numbers for counting. I think of them as the counting numbers, and certainly we can have 0 of some things, so we use 0 for counting, and then for me it makes sense to have 0 as a natural number. So it really, it's not an especially important distinction, but for us throughout MATH0007, 0 will be regarded as a natural number. As I mentioned before, bold Z refers to the set of integers. That's all of the whole numbers, positive or negative. There's no controversy here. People always use the integers to mean the thing which I've written here, so the set of all positive whole numbers, the set of all whole numbers, positive, negative, or 0. And finally, bold Q is the set of rational numbers, and that means the fractions a divided by b, where a and b are integers and b is non-zero, since it wouldn't make sense to divide by 0. Okay, that's our standard notation for sets of numbers. We use this all the time throughout 0007, so it's important you remember all of these notations. Let's now talk about subsets. So if we have a set y and another set x, then we say that x is a subset of y, and we write this notation here if and only if every element of x is also an element of y. Another way to phrase this is to say that x is contained in y. That means precisely the same thing, that x is a subset of y. You'll sometimes see a variant on this notation to indicate that x is a proper subset of y. That is, it is a subset and it's not equal to y. So if x is a subset of y, but x is not equal to y, and I'm going to come to a definition of set equality later, we write x is, and there's similar notation only with a cross through the line underneath, and we say x is a proper subset of y. You will sometimes see people use notation like this. So they may write x and then just this thing and then y. I don't like to do that because some people use this for being a subset and some people use it for being a proper subset. So it's confusing, and we will never, ever do this. Okay, let's look at some examples of subsets then. My next bullet point, the set containing 1 is a subset of the set containing 0, 1, 2. That's because there is only one element of the set containing 1, namely 1. That's also an element of this set. So every element in this set is also in the other set. And that means they fulfill the definition of being a subset. Similarly, the natural numbers are a subset of the integers because every natural number is also an integer. we use, as usual, the same notation crossed out to mean that x is not a subset of y. And so not being a subset of y would mean that x contained an element that y did not contain. For example, the set containing 0, 1 is not a subset of the set containing 1, 2, because 0, 1 contains an element which 1, 2 does not contain, namely 0. Finally, let's note a quirk of the empty set. For every set x, the empty set is a subset of x. So every set, absolutely every set, has the empty set as a subset. That's because the condition that every element of the empty set is also an element of x is vacuously true no matter what x is, because there aren't any elements in the empty set. So if you like, you can just regard this as a convention. You don't have to make logical sense out of it. You can simply regard it as a definition. But in mathematics, we often regard definitions like this as being vacuously true when we're insisting that in the subset definition, every element of the set on the left must be an element of the set on the right, and that's regarded as vacuously true when there aren't any elements on the set on the left. So a way to make sense of this is to think about the set of the definition of subset as being one that you need to falsify. So if you think that x is not a subset of y, then what you must do is produce an element of x which is not an element of y. So you have to prove x is guilty of not being a subset by finding an element in x which is not in y. But you'll notice that you cannot do this for the empty set because you can't find any elements in the empty set. The whole point of the definition of the empty set is that it doesn't have any elements. So from this point of view, you can't falsify this statement that the empty set is a subset of x, and therefore you have to regard it as being a subset of x, no matter what x is. Okay, moving on, we have a definition of set equality. And the definition of set equality is that x is equal to y means, by definition, x is a subset of y and y is a subset of x. In other words, x is equal to y if every element of x is also an element of y, and every element of y is also an element of x. You can think of that as x and y having the same elements in the sense that every element of x is also an element of y, and every element of y is also an element of x. Now this definition has some maybe slightly surprising and certainly very important consequences, which is that order and repetition don't matter to sets. For example, the set 1, 2 is equal to the set 2, 1. And the reason is that they fulfill the definition of set equality. So the only things which are in this set are 1 and 2. And those are also elements of this set. So that means the set on the left is a subset of the set on the right. But the same argument works backwards. Every element of the set containing 2 and 1 is also an element of the set containing 1 and 2. So we have that the set containing 2 and 1 is a subset of the set containing 1 and 2. They're subsets of each other, so they're equal. So just because of this definition of set equality, order in sets does not matter. 1, 2 is equal to 2, 1, and more generally, if you rearrange the elements of the set, you don't change that set. Another important consequence is that repetition doesn't matter. So for example, the set containing 1 and 1 is equal to the set containing 1, and again for the same reason. So every element of the set on the left is also an element of the set on the right, because the only thing which can answer yes to the question, are you an element of the set containing 1 and 1, is the number 1, and that is also an element of this set. So the set on the left is the subset of the set on the right, and similarly, the only thing which is an element of the set containing 1, the set on the right there, is the number 1. That's also an element of the set on the left, so the set on the right is a subset of the set on the left. They are equal. To show you some further examples, for example, 1, 2, 1 will be equal as a set to the set 2, 1. The only things in here are 1 and 2. So 1 is an element of that set, 2 is an element of that set. Nothing else can say yes to the question, are you an element of that set? And similarly, over here, the only things which can answer yes to the question, are you an element of this set, are 1 and 2. These sets have the same elements, so they are equal by our definition of set equality. Order and repetition don't matter to sets. Okay, for our last slide, this definition of set equality gives us a useful and extremely common way to prove that two sets are equal. So because two sets are defined to be equal if each is a subset of the other, if we're given two sets x and y, we can prove x equals y by proving that x is a subset of y and y is a subset of x. In other words, that every element of x is also in y and every element of y is also in x. This is actually very useful because it gives us a structure for our proofs that two sets are equal. It lets us split the proof into two logical parts, in the first of which we prove x is a subset of y by proving that every element of x is also in y, and in the second, we prove y is a subset of x by proving that every element of y is also an element of x. So this gives us a structure for set proofs. It's very useful, and you should follow it unless you have some particular reason not to. So the kind of default option, if you want to prove two sets are equal, is to do it by this two-step method. So let's do an example. Let capital X be the set. This is going to be the set of all integers. So let's say A in Z such that A is equal to 3k plus 1 for some k in Z. So that's an example of the set builder notation. And we're going to have y, let's just clear that equals sign up a little bit. Y is going to be equal to the set of all things. Let's use B this time, just to be clear. B in Z such that B is equal to 3 times L minus 2 for some L in Z. Okay, so some elements of X would be things like, what's in there? 4 is in there. 1 is in there. 3 times minus 1 plus 1 is minus 2. So these things are elements. For example, of course, it has infinitely many elements. And if we turn and take a look at Y, that contains some things like 3L minus 2. So for example, it would contain 3 times 0 minus 2. That's an element. It would contain 3 times 3 minus 2. So that is 7. And so on. Many other elements. Okay, well, I claim X is equal to Y. And I'm going to prove it using the method I've just described to you. So this double inclusion method where you show that X is a subset of Y and then Y is a subset of X. And you do that by showing every element of X is also in Y and every element of Y is also in X. Okay, so we'll lay our proof out by doing two inclusions. So first of all, I'm going to show that X is a subset of Y. So I'll write the subset notation in this direction to remind me that I'm showing X is a subset of Y. So how are we going to do this? Well, let's let A in X, and I have to prove that A is an element of Y. So by definition of being an X, A is equal to 3k plus 1 for some k in Z. And I want to show that actually this thing is in Y, so I must show that A can be written as a multiple of 3 minus 2, where that multiple is an integer multiple of 3 minus 2. Well, that's easy because A is also equal to 3 times k minus 1, plus 1 minus 2, right? If you expand that, you get 3k plus 3 minus 2, which is 3k plus 1. So that is an integer multiple of 3 minus 2. Therefore, A is in Y. So we've proved that every element of X is also an element of Y, and therefore X is a subset of Y, right? And now we have to do the other half of the proof. So I'll label the other half of the proof with a set subset symbol the other way round to remind me that this time I'm proving Y is a subset of X. So this time, well, it's going to be just the same. Let's let B be an element of Y, and what I've got to do is prove that B is also an element of X. So if B is an element of Y, then B is equal to 3L minus 2 for some L in Z. Now again, we can just do a simple rearrangement. B is equal to 3L minus 1 plus 1, because if you multiply this out again, you get 3L minus 3 plus 1, which is 3L minus 2, which is B. But now this is a multiple of 3, an integer multiple of 3, because L minus 1 was an integer. And similarly, up here, K plus 1 was an integer. So we've got an integer multiple of 3 plus 1. And A is the set of all integer multiples of 3 plus 1. So A is an element of X. And we've proved every element of Y is also in X. So we have proved Y is a subset of X. Now we've finished our two-step procedure. We've shown that X is a subset of Y and Y is a subset of X. And therefore that X is equal to Y according to our definition of set equality. So this is the standard method of doing proofs of equalities of sets. We call this proof by double inclusion, because inclusion is another word for something being a subset of something else. And we've proved two subset relations here, so we've done a double inclusion.